Hello, my name is George Paris, and I've been watching YouTube videos. And one of the things I've noticed recently is that there's a fair number of videos out there of people who actually have credentials in the physics world who are raising skeptical views of the current state of particle physics. Now, this is kind of interesting to me because about a year ago, I made a video in which I raised concerns about the viability of a particular experiment having to do with neutrinos, or it wasn't really an experiment, it was a hypothesis about neutrinos. And I've always felt that that was uh, a substantial problem. And I think the reason I'm bringing it up now is because I think it is really sort of the point of departure for particle physics into this sort of never land where everything is tied to a statistical analysis of very dubious data, in my view. I'm losing my voice here, I'm afraid. In any event, let's see how this goes. Okay, I'm a chemist. Chemists have superficial knowledge of atomic theory. And I was working on a book a while back having to do with atomic theory. And that's the book, and it's available on Amazon for moderate prices. And what I discovered, of course, is that as you're looking at the physicists who developed this, that physicists, like chemists, are humans with all sorts of personal demons and ambitions, strengths and weaknesses. And the real history is not as simple as typically related in most textbooks. Pardon me. I was impressed in particular with the honesty of Ernest Rutherford. He carefully designed experiments and published his observations. Some of these reports, such as the transmutation of elements back and forth during radioactive decay, must have seemed much like a supernatural phenomenon. I mean, here you've got one day you have one element, the next day you've got a different element, the next day you're back to the first element. Now, a lot of people would just throw that experiment in the trash and never report it. But Rutherford followed up, looked at it very carefully, did very careful work, and ultimately ended up publishing some very important papers. Now, Rutherford was an experimentalist. He was also a guy who thought deeply about these problems. And he had a number of relevant quotes, but the one I like most of all is if your experiment needs statistics, and most of the current experiments need statistics, you ought to have done a better experiment. Now keep that in mind as we go through the following work. Now, as I compile my history, I discovered something called the beta electron problem. This was from 1920 to 1933. People started observing these beta electrons coming out as a form of radioactivity of certain elements, certain isotopes. And what they expected, they said, hey, this must be a quantized problem or a phenomena. And they expected to see something like you see here on the right, a single peak of some energies. There'd probably be a spread a little bit, but they were expecting a single peak. Well, what they got was this. It's actually a spectrum of energies from a maximum Emax kinetic energy of the beta electron down to zero. And you see this difference in probability or intensity of the beam of beta electrons changes as you look at different energies. So this was a great conundrum. Why, if this is supposed to be a quantized phenomena, why are we getting this spectrum? Now, Rutherford's group, that would be Ellis and Mott for the most part, and Meitner's group, that would be Meitner and a herd of other people, looked at this, and they argued back and forth about what it meant, but they did a number of experiments over about a 10-year period, and they concluded that they agreed on the results of the experiment. There was a spectrum of energies, but neither group had a rational explanation for that. Now, they challenged one another. They put up various proposals. One would put up a proposal, the other would attack it and see what happened, but they never came up with an explanation that made any real sense. Now, this was getting to be fairly desperate, and some people were even starting to say, well, maybe conservation of energy is not instantaneous. Maybe it's conserved only as a statistical phenomena. And fortunately, nobody was willing to buy into this, that conservation of energy was a closely held and very important concept. And so people went forward and they just sort of left this hanging. Now, things to keep in mind, we're talking early 1930s for the most part. At that point, the nucleus was modeled primarily as a point charge. It was viewed as being very tiny, and I think everybody who thought much about it quantitatively thought in terms of it being a point charge. Also, the neutron was not known at this time, not until 1932 with James Chadwick. Okay, so what happened? How did this all sort of go awry? We have good people doing very careful work. How did this thing seem to go off the rails? Well, this gentleman is Wolfgang Pauli, and he had an idea. Hey, a particle cannot be detected. That would explain it. Now, I'm going to get into this quite some detail, but Pauli was basically a very interesting guy who currently has a very high reputation. People view him as one of the premier physicists of the 20th century. This guy is supposed to be right up there with Einstein. All right, so let's look at Wolfgang Pauli a little bit, because this is the part people don't tend to look at very much. Pauli was born in Vienna, Austria, into a well-connected family. I think Ernst Mach was the godfather. Eventually made it into the laboratory of Arnold Sommerfeld in Munich, Germany, in 1918. Now he's 18 years old when he goes to Sommerfeld's lab. His lab mate, by the way, was Werner Heisenberg. And Heisenberg has described him as being something of a playboy. He said that Pauli liked to stay out, drink, carouse in the bars and cafes all night, coming home late, showing up at the lab about noon the next day. Sommerfeld wasn't happy with this. On top of that, Pauli was notoriously poor as an experimentalist. That's probably why his advisor, Sommerfeld, asked him to write a paper on Einstein's theory of relativity targeted at a popular audience. Now, Pauli did this, and it was published in 1921. You have to put all of this in context of what's going on. Don't take it all at face value. You have to appreciate these people have ambitions and have motives that don't necessarily pop out of the textbooks. At this time, this was 1921, Einstein was hoping to win the Nobel Prize based on the fact that Arthur Eddington, a cosmologist, astronomer, had taken some photographs during a solar eclipse. This would be May 29, 1919, on the island of Principe, that's off the coast of West Africa. This confirmed Einstein's prediction concerning relativity, having to do with gravity lensing. Basically, the light from the distant stars as it passed by the sun, which you could see during an eclipse, was being bent. It made it look like the stars were displaced. And so this was looked like a major milestone, looked like something that Einstein deserved the Nobel Prize for. And Einstein was, of course, highly motivated because he'd already promised the money from this Nobel Prize to his first wife, who had a couple of kids with him. So Einstein certainly wanted this to go forward. So in this situation, do you expect Einstein to say anything bad about a widely read description of his theory at this time? I don't think so. Of course not. Einstein is not going to trash this report by this bungling 21-year-old graduate student author. Okay, so basically Einstein went out and had a lot of nice things to say about the report because it was in Einstein's advantage to do that. And it necessarily rose up or pulled up the author. It made Pauli look like a very bright guy who Einstein thought was very great. So, and that patina that was placed on Pauli by Einstein's comments carried him through his entire career. It really did. All right. So, in spite of Pauli's unimpressive work in the lab, his thesis was very mediocre. People don't even talk about it. He received a PhD in 1921 and he was able to find work in a series of top European laboratories. I think he worked with at different times with Bohr and Born and other folks. And he sort of followed along where Heisenberg had been. Anyway, so by the 1920s, Pauli managed to get a teaching job in Hamburg, and he was there in 1923, 1928. Now, he was not doing anything that anybody cared much about. He was literally just teaching, not doing anything research-wise that people got excited about. He was drifting into obscurity. The patina that had been provided by Einstein had worn off, and he really didn't accomplish anything on his own between 1920 and 1930. Also, it turns out that Pauli had he was a smart guy. He had a quick wit, and he was, frankly, I think he was a bully. He basically criticized other people's works, turned their words on them, things like that. He was not, frankly, a person who was well liked. Now, put this in context again. Germany in the 1920s was undergoing hyperinflation. People were carrying, wheelbarrow loads of paper bills to buy a loaf of bread. But Pauli had a steady salary as a professor, and apparently was indexed to the cost of living or something, and so he was doing okay. So through the economic upheaval of the 20s in Germany, Pauli was able to enjoy the nightlife in cabarets and bars, just like he did as a graduate student. Now, there's a very interesting report. It says you can find this website on YouTube, not on YouTube, but on the internet. 17 reasons why Germany's Weimar Republic was a party lover's paradise. Obviously, this is cut out for Pauli. And I'll give you a quote there. As the famous journalist Hans Oswald remarked at the time, most dance halls are nothing but markets for prostitution. Many of the dancing girls at the cabaret bars and dance halls could be taken home or just into the back room for the right price. Okay, so keep that in mind. That's the context in which Pauli is living in Germany with a pretty good salary, good job. All right, so if you read Pauli's biographies, about all it will say is that in 1929 he met a woman named Kate Margaret Zepner. I can't pronounce any of that. Usually described as a dancer in late 1929. Okay. Now, what did a dancer do in 1929 in Germany? Well, anyway. So they got married. I think it was it was either November, December 29. Now, the Nazis were coming into power in Germany. Pauli identified as Jewish. He moved to Austria, took his wife with him, and she divorced him in late 1930. Okay, so this marriage lasted about a year and didn't go down well. Now, at this point, Pauly is very down on his luck. He's like been out of the limelight for 10 years. He's in Austria. He had to move. He moved from Austria to Switzerland, to Zurich. Took a no special job. He was not doing anything special experimentation. People had at one time considered him to be Einstein's successor, but he was at this point very desperate for attention. His personality required that he have attention. So he wrote a letter that was bound to get some attention. There was a meeting of all the leading atomic physicists in Tübingen, that's in Germany, I believe, to which no one considered Pauly worth inviting. Okay, so he decided to inject himself into this meeting. He proposed a solution to the beta electron problem that was so obvious that if it had not been so ridiculous, anybody would have thought of it. He claimed to be considering to publish the theory. He dropped names like Dubai. He fancied himself too indispensable in Europe to attend the scientific meeting. And frankly, Pauly's letter is pretty much grumbling. He's looking for attention. He's basically begging for attention. But, like I said, Pauly was pretty much a bully with a quick wit. And that's not making me up. I don't have time to go through all the details. This citation does, in fact, go through a number of instances, and I found, I think, a couple of others. He was really pretty cruel, arrogant, pretty much unbelievable ego. This is the actual letter. I don't have time to read the whole thing. Look at the stuff in bold here. Concerning the continuous beta spectrum, the possibility that the nuclei there could exist electrically neutral particles, which I will call neutrinos. That term, by the way, was not invented at that time. Somebody's obviously edited it at the time. He called them neutrons, I'm sure, that have spin a half and obey the exclusion principle, and that further differ from light quanta in that they do not travel at the velocity of light. The mass of the neutrinos may be of the same order as the electron mass. By the way, electrons were regarded as being very tiny, almost massless, and in any event not larger than 1/100th of a proton mass. The continuous beta spectrum would then make sense with the assumption that in beta decay, in addition to the electron, a neutron, I think he would have said neutron, is emitted such that the sum of the energies of the neutrino, again, not invented at this time, and electron is constant. Now, he goes into some more discussion here, dropping some names, whatnot. At the very end here, this sort of drives me crazy. He says, unfortunately, I cannot personally appear in Tübingen since I am indispensable here in Zurich because of a ball on the night of the December 6th, 7th. With my best regards, you, signed Wolfgang Pauly. Okay. A very off the wall and self-serving and arrogant letter. All right. Pauly's name particle was called a neutron, but when the real neutron was found in 1932 by Chadwick, it was demoted to being the neutrino. At the time, in 1932, no one in mainstream physics seemed to be interested in Pauly's absurd idea. Nonetheless, by 1945, when he won the Nobel Prize, Pauly was recognized as the first to recognize the existence of the neutrino, an uncharged and massless particle which carries off energy in radioactive beta disintegrations. Those statements sort of fly in the face of everything. You got a massless particle carrying off kinetic energy, and it's uncharged. So what motivates it is just hard to believe. Discovery of the neutron also had another effect. People had been shooting alpha particles and maybe protons at nuclei, and because the alpha particle, the proton has positive charge, and the nucleus has positive charge, you just couldn't get them together. I mean, they would veer off But this neutral particle seemed like a possibility for sending it into the atomic nucleus. And then the idea was, okay, let it go beta decay. And when it does that, it'll create a proton, which increases your atomic number by 1 increment. So this would be a way to make heavier elements. And Fermi got interested in this. Enrico Fermi, I'll talk about Enrico Fermi in a minute. And this would, if you started out with uranium, which was the heaviest known element, you could potentially make elements that nobody had ever seen before, the so-called transuranics. And so Fermi got involved in this and started doing this work in the 1930s. And between 1930 and 1930, I guess it's 32, 33, and 1939, he was considered to be the leader in proton activities, and that sort of stuck with him. Let's talk about Enrico. He was from Italy, and in many ways he was very similar to Wolfgang Pauli. They were both terrible experimentalists, okay? Fermi was actually a very good mathematician and was interested in theoretical physics. When the discovery of the neutron, as I mentioned, in 1932 occurred, his attention was drawn to Pauli's concept of the tiny new particle that could not be detected because it rarely interacted with matter and yet could carry away kinetic energy when a neutron decayed to a proton and electron. In other words, Pauli had access to the idea that, Fermi had access to the concept that Pauli had created out there. Now, using his math skills, Fermi wrote a paper in which he created a quantum mechanical description of a massless particle that could carry away kinetic energy, not interact with matter, and explain the observed beta electron kinetic energy spectrum. Okay? Now, this paper was originally submitted to Nature, British magazine, but it was rejected because the referees thought it was like too far from reality. People were still not buying this idea. Now, undaunted, Fermi sent the paper, actually sent it to some Italian journals, and he also sent it to Zeitschrift für Physik. And in January 1934, it was published. And I regard this as Fermi's most embarrassing mistake. I'm saying it's the most, that implies that there are other mistakes. Here we go. Even if you're a physicist, you may not know that what I consider to be Fermi's serious mistakes. I think any of these should have ended his career. One, he dignified the neutrino, 1934, see above and below. Now, two, claims of producing transuranic elements, 1939, for which he won the Nobel Prize just before Otto Hahn proved it wrong, and building and taking a reactor critical, December 1942, under the bleachers of the football stadium in Chicago. That would be a inappropriate thing to do, I believe. This is worse. That is to say that the number one is worse because it cannot be proven to be wrong. That's a problem. In science, you need to have things that can be proven to be wrong. That is to say, if you've got a real hypothesis, you can prove it to be wrong. The whole problem with the neutrino is you can't prove it's wrong. Okay, now I'm not a genius, but I have the advantage of knowing things that Rutherford and Meitner did not know in 1930. Among these are that although the nucleus, 10 to the minus 15 meters, is small relative to the atom 10 to the minus 10 meters, it is not a point charge. The nucleus contains discrete neutrons that decay to give beta electrons. Free neutrons are unstable and decay with a half-life on the order of 10 minutes. Which leads me to ask some questions. Why are some neutrons stable in the nucleus and others not? Why does a nucleus absorb some of the beta electron kinetic energy as a torque? Why doesn't it? Apparently nobody thinks about there being a torque. And then why shouldn't Gauss's law applies? Now, let me go into that a little bit. If the nucleus is not a point charge, it is unlikely that a electron flying out of the nucleus, a beta particle, is going to have a trajectory that can be traced back through the center of mass of the nucleus. The odds of that happening is real smalls. So, you can't just say, well, hey, the nucleus is much bigger, because you don't have to move the whole nucleus, you just have to turn it a little bit. So there's probably a torque involved here someplace. And Gauss's law, basically, if you do electrical stuff, you know that basically if you have a surface, then everything within that surface counts as a part of the charge. You can assume that all the charge is concentrated at the center. But if you have a spherical charge, as you penetrate into it towards the center, the effective nuclear charge drops off drastically. Let's think about that for a minute. Here's the beta decay torque issue. You'll notice if the blue color there is if that's the nucleus, and we have a neutron pop to a proton and kick out an electron somewhere in that thing, the odds are very unlikely that the electron trajectory is going to be such that the recoil force is through the center of mass. It's almost certainly going to create some sort of a torque. That torque may create a magnetic moment, and that magnetic moment may be observable as a nuclear magnetic resonance phenomenon. Okay, so that's one thing. If the nucleus is not a point charge, most of the time the electron will fly off in a path that does not go through the center of mass. I've said that about 3 times. Depending upon the nucleus is, when it decays, there should be some sort of torque applied to the successor nucleus. That torque equates to a nuclear magnetic moment that might be detectable. These magnetic moments are probably quantized. But even more important, we must consider the electrostatic field experienced by the escaping beta electron. And here's what I've drawn. This is the nucleus. It's not the atom. It's the whole nucleus. And what I've done here is I've superimposed what I call Gauss surfaces over it. And if you were right at the center of the nucleus, as to say the center of charge, when that beta electron is created, it does not experience any electric charge because there's no charge inside of it, that is to say towards the center. And so it's going to just come flying out of there with all of its kinetic energy intact. But as it moves outward from the center, and I've shown it here, this blue circle is like I've moved out a certain distance from the center. That area within the blue circle represents the charged area that is going to have to be overcome by the beta electron. And so as the electron is created further and further out on this, it's going to experience more and more electrostatic attraction. It's going to be harder and harder to escape from the nucleus. As a matter of fact, I believe this is what stabilizes neutrons in atoms. Neutrons out in free space disintegrate in about 10 minutes, half-life about 10 minutes, but they can be infinitely stable inside of nuclei. And so what is magic about the nucleus that prevents the neutron from decaying? And I think it probably has to do with the fact that at some point the neutron is stabilized because there is so much electrostatic attraction that it cannot escape, and it has to return and hook up with some proton back in the nucleus. Okay, so anyway, I've superimposed on that an axis. On my vertical axis, I talk about the probability of finding a neutron inside of a particular dr increment. That is to say, a infinitesimal part of the radius of this spherical charge. And as you go from the center of the atom out towards the sides, the volume of those shells, those are concentric, like bird nested shells, they're going to get bigger. Okay. And at some point, you will come to a point where the neutron is stabilized. It says it can't escape because of the overall charge. And you end up getting this type of a curve. The red dashed line basically is a hypothetical example of what you would expect if the neutrons were popping out of the nucleus from different points, starting at the center of the nucleus, where there's a very low probability of being exactly at the nucleus, out to some range where essentially the kinetic energy that the electron will have will be essentially zero, because it has the electrostatic attraction back to the nucleus. I call that, for lack of a better term, I just call that volume, which is represented in the blue and the brown there, as the sweet spot where the beta electron can escape. You go outside of that, and you have so much nuclear charge the beta electron can escape. Simple idea. Kinetic energy is on the horizontal, and the probability is on the vertical. In most cases, the neutron inflation energy, and that's what I call it, the neutron turning into a proton, is inflating. And I'm introducing the concept of the zero energy level. In other words, if we talk about hydrogen-like energy levels, we start with n is equal to 1 and go up from there. But if you think about the neutron being related to a proton, then the electron is intimately involved with the proton, and you sort of have a model of the atom, the plum pudding model, if you go all the way back there, where the electrons are buried in this positive charge. Actually, Rutherford described this as the neutral doublet, and I think that possibly is a very good description of it. Again, I liked a lot of things that Rutherford did and said. So anyway, this is an energetic process. And the way a chemist, and I'm a chemist, would come at this problem or this issue. And on the next slide, I will show you the diagram, but I consider two activities. First, you've got A is some isotope of atomic mass X, okay? So the first step is this isotope flashing. There's a inflation of one of the neutrons to give you an activated complex. That's a term that chemists like, in which X is now X minus 1. You've gotten rid of, you've turned one of the neutrons into a proton, and that proton is actually part of a hydrogen atom that's superimposed on the isotope. And so you've got this X minus 1 as the atomic number, atomic mass, but you have superimposed on it, you have this hydrogen atom. And so that energy is all still retained within that activated complex. Then that activated complex basically spits out a beta particle. When it does that, you no longer have that hydrogen atom. Now you just have a proton, which keeps the atomic number the same, but you have actually the atomic number is going to go up, but the atomic mass is going to stay the same. And you have the new isotope, which is D. It's going to have a positive charge because the beta electron is left, but it can pick up an electron any place. The energy, by the way, of ionizing this second isotope is trivial compared to the nuclear phenomena that are going on here. Here's a different representation. It's not to scale or anything, but basically I take the binding energy between bismuth and bismuth is the classic example. It's the one everybody studied. Take this binding energy between the bismuth 210 and the polonium 210, and the neutron inflation energy, bang bang. You go up to this complex in which you have essentially reduced the atomic mass of bismuth, but you have superimposed on it a hydrogen atom now. That hydrogen atom spits out a electron, beta electron, with a certain, carrying as much ionization energy as it can. And then concurrently, the bismuth is now converted into polonium. And you have the difference between these energies is observed as the kinetic energy for the beta electron. All right. Now, these are not to scale. This term, the red line there, that is greatly enlarged by factors of 1,000, I guess, or more than 1,000. Okay, so I went back through, put numbers in here, and this was one of the things that convinced me that, hey, this might actually make some sense. If you look at the neutron going to a proton electron, you have a loss of mass. That results in a certain amount of kinetic exothermal energy. This would be like 780 keV. That's got to go someplace. It's going to end up as the neutron or the electron kinetic energy, if nothing else. At the same time, you've got this bismuth going to polonium. There's binding energy differences. You add those two numbers together, and you come up with a calculated kinetic energy, maximum kinetic energy for the beta electron as 1159 keV, and those are right. All these numbers have some. You'll find different numbers for different parts and different sources, but these are all pretty good to at least 3 significant figures, pushing 4 significant figures. And so you're looking at 1159 versus 1161. Okay, so these numbers basically add up. The ionization energy that is not included in this calculation is about 0.008 keV. In other words, it's about 8 electron volts, which is, like I said, pretty much nothing on the nuclear scale. Thus, there is perfectly reasonable reason for beta electrons to have a spectrum of kinetic energies. You don't need something magic to make that happen. And the arguments are simple, and they use classical physics. Moreover, if you take this interpretation, some interesting questions come up. Let's talk about the neutral doublet theory of neutrons. Let's talk about the mechanism and rate of beta decay. I think you can start trying to think about a mechanism for why beta decay occurs. How about the stability of alpha particles? Now you can start thinking about the stability of alpha particles. And you talk about nuclear stability in general. And the quantum mechanics of hydrogen molecules and neutrons. How do they compare to one another? Now, here's where things sort of go crazy. After World War II, that would be by 1945, Fermi and Pauli both rose in power and prestige and influence. Like I said, Pauli was still playing the Einstein card. Einstein was getting into the end of his career. I think he was probably taken advantage of in some cases by Pauli. And he didn't want to contradict himself over the years that he had said nice things about Pauli. And Pauli had made some theoretical suggestions about this so-called Pauli exclusion principle. So Einstein, I think, nominated him for the Nobel Prize, and he got it. Now, Fermi, as I've already trashed his biography, I think he made some mistakes. He the thing about both of these guys, Fermi and Pauli, is they were both in 1945, 1950. They were both in the peak of their careers. They're both like 45 to 50 years old. Whereas the other guys like Oppenheimer and some of the others were getting sort of in the end of their careers, like Einstein. And so they were not, these were the young Turks who were sort of taking over and got a lot of credit and a lot of influence politically and academically. Now, the neutrino theory, in my view, has all the hallmarks of a bad idea. Okay, every time you look at something, you find that there's a problem. Okay, for example, at one point they thought the sun had stopped working because they couldn't find enough neutrinos, and this caused an addition to the theory. Then, at one point, not that long ago, CERN thought that neutrinos were arriving before light. And this also shows up in some of the supernova work. I won't go into all that. But, what did they did? They started to add to the theory, but they said, no, we can't have neutrinos going faster than light. So let's go back and we'll find the experimental problem. And they found the experimental problem, and that went away. Okay. And, neutrinos can only be observed statistically. I'm not going to go into the Cohen-Rains work and other work and all the ice cubes and beta detectors that are out there. But, these are all statistical experiments. Most of them don't seem to work to start with. People tinker with them. Cohen-Rains worked at Los Alamos. They worked at Hanford. They ended up at Savannah River. They kept tinkering with this thing. Finally, they did a number of things and were able to get statistical significance. And when they did that, they stopped taking data and published their paper. That's what you do when you're doing things statistically. When you have statistical significance, you stop taking data and you publish your paper. Now, only people with big detectors can observe neutrinos, so send them money. That's a big thing these days. And that brings us to the point is, wait for it, there it is. Without these papers, that is to say, without the letter from Pauli and the publication by Fermi, no one would have ever looked for neutrinos, and no one would notice any problems caused by their absence. That's the remarkable thing. And this whole area of particle physics has taken off for neutrinos and multiplied and expanded, and that is what the people who actually are more credible and knowledgeable than I am are bringing up in YouTube videos and various presentations I see. So with that, I'll leave you. One last thing. I will speculate, if I went back and calculated if I took that 161 keV kinetic energy of that electron and assumed that the charge of the nucleus of a bismuth atom was symmetrical, homogeneous and symmetrical, I would go back and I would do this arithmetic, and I could calculate that what I would call the Gauss radius, that would be the maximum radius of escaping, would be about 5.2 times 10 to the minus 15 meters, which is interesting because the assumption about the radius of large, heavier atoms is that they're about 10 times 10 to the minus 15 meters. So the speculative guess and my speculative calculation would suggest that about 12% of the volume of the nucleus of the bismuth atom would be what I call the sweet spot. That would be the volume from which the beta electron could actually escape. So I'll just leave it there, and you can start criticizing. Oh, I would, if we're going to go into this beta decay thing, if we're actually starting to think about it, maybe you should look at what is stable and what's not. It's interesting hydrogen, deuterium are stable. Tritium is not. Helium-3, as I understand, is stable. Helium-4 is certainly stable. Alpha particles are certainly stable. So a chemist would probably say something like, not enough positive charge in tritium to keep the neutron from inflating. But I'll leave that.